All right, let's get right into it. Today, we are going to demystify the absolute mechanical magic happening right under the hood of almost every vehicle on the road. We're taking a journey straight into the heart of the internal combustion engine. Because whether you're just cruising to the grocery store or operating massive industrial machinery, there is a literal ballet of precision engineering happening completely out of sight. And by the end of this explainer, you're going to understand exactly how it all works. Okay, let's dive into this. Have you ever actually stopped to think about what happens the exact second you turn the key in your ignition or push that start button? I mean, how does a single drop of liquid fuel transform into the roaring power of a machine that weighs thousands of pounds? Well, it all comes down to a perfectly timed cycle of physics and mechanics operating at frankly incredible speeds and under immense pressure. Here is our roadmap for today. First, we'll look at the fundamental pulse of the engine. Second, the anatomy of power transfer. Third, valve timing and overlap. And finally, we'll step into the operating room for some hands-on maintenance.
Starting off with Section 1, the fundamental pulse.
So the engine actually produces power in 4 distinct stages: suction, compression, power, and exhaust. Or, if you want a highly memorable trick that mechanics have been using for decades to remember this combustion cycle, just think suck, squeeze, bang, blow. Let's break that down. First, the piston moves down, literally sucking in fresh air, and fuel if it's a gas engine. That's your intake stroke. Then the valve snaps shut and the piston pushes right back up, squeezing that trapped air and drastically increasing its pressure and temperature. That's compression. Next is the bang, the power stroke. The fuel ignites, creating a massive controlled explosion that violently forces the piston back down. And finally, the exhaust stroke blows all those burned gases out of the cylinder so the whole crazy cycle can start all over again. So we've got these micro explosions happening, right? But how does that actually move a vehicle? Let's figure that out in Section 2, Anatomy of Power Transfer. Now, what's really interesting about this slide is the specialized design of the piston itself. It's not just some solid, dumb chunk of metal. The top flat surface, called the piston crown, takes the direct, brutal force of the burning fuel. Just below that, we have the rings. The top and second rings are your compression rings. They physically slide against the cylinder wall to completely seal in those high-pressure gases so they don't leak down into the engine block. Below those is the scraper ring, which acts just like a tiny squeegee, pulling excess oil off the cylinder wall. And finally, the lower body, or piston skirt, maintains critical alignment so the piston doesn't wobble around as it rockets up and down. Let's trace the actual chain reaction of movement here. The force hits that piston crown, violently pushing it down. That force transfers right into the center of the piston, passing through a hollow steel tube called the piston pin. That pin then connects to a connecting rod. Honestly, the best way to visualize this is to think of the connecting rod and the crankshaft just like your leg and a bicycle pedal. Your leg pushes straight down, right? That's linear force. But the pedal and the crank convert that straight downward push into a continuous circular rotation. The connecting rod is basically acting as a lever arm turning the crankshaft, beautifully transforming an up and down explosion into the rotary motion that will eventually turn your wheels. But here's the catch. For those explosions to be powerful and efficient, the engine has to breathe perfectly.
Which brings us to Section 3, valve timing and overlap.
You might naturally assume that when the intake valve is open, the exhaust valve is strictly closed, and vice versa. It just makes sense, right? But engine designers actually use a brilliant little trick called valve overlap. This is a very brief, precisely engineered window where both the intake and exhaust valves are slightly open at the exact same time. And you might be wondering, why on earth would they do that? Well, because the rush of fresh incoming air physically helps push the absolute last remaining stubborn exhaust gases right out of the cylinder. It's an effect called scavenging. It purges the cylinder beautifully and reduces the pumping work the engine has to do, which greatly improves efficiency, especially when you're running at higher speeds. And this brilliantly illustrates exactly how that timing maps out. We're looking at a spiral diagram tracking the cycle. You can see top dead center, which is the absolute highest point the piston reaches, and bottom dead center, the lowest. Check out the markers for intake valve open and exhaust valve close. Notice how they overlap right up near top dead center, caught perfectly between the exhaust and suction phases. This visual really proves that the 4 strokes aren't just rigid, separate blocks. They actually blend into each other in this highly choreographed, continuous sequence. Now, to control these valves, especially in heavy-duty diesel engines, engineers often use double or nested valve springs. Diesel engines are a whole different beast. They operate at massively high pressures compared to your standard gas car. So, they actually need the heavy tension of 2 springs to force the exhaust valve completely closed against all that intense pressure. The dual springs also stop the valves from basically bouncing around when the engine is running fast, but most importantly, it's a fail-safe. If one spring snaps under all that immense stress, the second one keeps the valve from dropping straight down into the cylinder, which, trust me, would instantly cause catastrophic engine failure. So, knowing how it all works is one thing, but how do we actually maintain it when things go wrong?
Let's scrub in for Section 4, the operating room. In the operating room, mechanical precision is literally everything. Take the tappet clearance, for example. That's the tiny, microscopic physical gap between the valve mechanism and the valve itself. This gap has to live in a super tight Goldilocks zone. If the gap is too large, the valve opens late. You end up with this terrible clattering noise, excessive heat trapped in the cylinder, and a noticeable drop in power. But if the gap is too small, the valve opens prematurely, or worse, it never fully closes. You lose all your compression, your power just vanishes, and those leaking hot gases will literally burn up your exhaust valves. It has to be absolutely perfect.
But wait, before we can adjust anything or take the engine apart, like, say, if we needed to remove the cylinder head, we must strictly observe some rigorous safety checks. Seriously, an engine that recently ran is a major hazard zone. First, you absolutely must allow it to cool to avoid severe burns. You disconnect the battery so a rogue spark doesn't trigger an electrical short. You have to drain off the scalding coolant and oil and explicitly relieve any trapped cylinder pressure before you even think about turning a wrench, or you're risking a highly pressurized blowout. Once it is completely safe, the surgical procedure to remove the cylinder head can begin. After stripping away all the external hoses and rocker arms, the most critical step is the third one on your screen, loosening the bolts in a precise, gradual sequence. You can't just take one bolt all the way out and then casually move to the next. No way. You have to follow a manual specified pattern, usually starting from the center and working your way outward, loosening each bolt a tiny bit at a time. If you ignore this sequence, the uneven release of pressure will physically warp that heavy metal cylinder head, completely ruining it.
Okay, so to set that perfect Goldilocks tappet clearance we talked about earlier, a mechanic will actually rotate the engine by hand to find top dead center on the compression stroke. That's the exact moment both valves are fully at rest. Then, using a specialized tool called a feeler gauge, which is just a precisely measured ultra-thin strip of metal, they slide it right into the gap. The mechanic then adjusts a set screw until there is just a slight drag on the feeler gauge when they pull it out. They lock it down, double-check it, and move on to the next valve. It is an act of pure, hands-on mechanical feel and precision.
So, what does this all mean for us? We've gone all the way from the basic intake of fresh air down to adjusting microscopic valve gaps with feeler gauges. The very next time you're sitting at a red light, I really want you to just feel the hum of the engine. Think about the millions of perfectly timed micro-explosions happening right beneath your feet every single minute, contained by tiny metal rings and precisely tuned springs, keeping that massive machine from literally tearing itself apart. It's incredible. But as the world rapidly pivots toward electric vehicles, one really has to wonder, will this intricate mechanical ballet soon be a lost art, or will internal combustion somehow evolve to survive? Thanks so much for joining me on this explainer, and keep that curiosity fired up.